Clear as mud? Okay. Let's think of some other cool things. Okay? All right. Here's V versus S. All right? V versus S has a sigmoidal shape to it, and this is explaining some things that really get beyond our need to know. Basically, for our need to know, all we worry about is the fact that a sigmoidal shape is not indicating cooperativity. It is a hyperbolic curve, is not indicating cooperativity. A sigmoidal shape is indicating cooperativity. And we'll leave it at that. Okay. Now, there's other things about enzymes we would like to know. All right? I talked about how the affinity of the enzyme changed in that allosteric enzyme. When I say affinity, I'm talking about attraction for. It's kind of like what happens down at Squirrel's on, say, Friday evening. Okay? As the beer goes up, the attraction for members of the opposite sex goes up as well. Okay? It happens. Okay? And it changes. Right? It's changing. All right? Well, what we would like to know down at Squirrel's is what is the average attractiveness of one to the other. That's kind of what we'd like to know here, because we're kind of weird people. Okay? We want to know this answer. Well, that's what we'd like to know about an enzyme. How much does the enzyme attract or want its substrate? That's what we want to know. Okay? We want to have some measure of that. How do we measure that? Well, it turns out there's a quantity that we use to measure it, okay, that's called Km. Okay? Km, that stands for the Michaelis constant. No, you don't need to spell that. Okay? Just Km is all you need to worry about. What is Km? Km, I'm going to define it for you, and then I'm going to tell you how we get it. Km is a measure of the affinity that an enzyme has for its substrate. Km is a measure of the affinity that an enzyme has for its substrate. Now, let's think in real terms about what that means. Let's imagine that I have an enzyme that I've just isolated, and it catalyzes a reaction on, let's say, ATP, just to keep it simple. Okay? And let's say I have an enzyme that's been sitting around in my lab for a long time, and it also catalyzes a reaction on ATP. And I want to know, do these two enzymes have the same affinity? Okay? Because I'm a weird guy again. It's the squirrels thing, right? I want to know. Okay? Let's imagine, if you will, that, well, I'll tell you the way that we do it is we have to do a plot of V versus S. And I'm going to explain, I'm going to get to that in a minute. But I want to throw a couple theoretical situations at you. The way that we do it is not by measuring Vmax, but rather by measuring Vmax over 2. Vmax, remember, measures velocity. It doesn't measure how much the enzyme wants. It might take a ton of enzyme to get up to Vmax. Okay? So it's very hard to compare the amount of substrate it takes to get to Vmax to give me any useful information, because in both cases it's going to take a ton. However, to get halfway there, it's not so difficult, because the enzyme is not overloaded with substrate. The enzyme is not overloaded with substrate. I can measure and I can compare those very readily. So I want to think not about Vmax, but about Vmax over 2. Okay? The question I'm asking is, how much substrate does it take to get to Vmax over 2? How much substrate does it take? All right? Here's my two enzymes. Enzyme number 1, sitting in my lab. Enzyme number 2, I just isolated. Both react on ATP. Enzyme number 1 takes 10 millimolar concentration of ATP before it reaches Vmax over 2. Enzyme number 2 takes 5 millimolar concentration before it reaches Vmax over 2. 10 millimolar here, 5 millimolar here. Which one has greater affinity for its substrate? It's number 2, because it takes less to get to half Vmax. It's literally grabbing that substrate. God, I love you. I love you. I love you guys, right? Low Km means high affinity. Low Km is high affinity. Now, we don't have to mathematically derive why Vmax over 2 is the critical quantity. But we do need to know how we get Km, because I will ask you this on an exam. I'm going to tell you. Okay? How do we determine Km? We determine Km by measuring the concentration of substrate that it takes to get to Vmax over 2. The concentration of substrate that it takes to get to Vmax over 2. On the exam, at least a quarter of you are going to tell me the following. Km is Vmax over 2. And if you look what you just wrote down, that wasn't what I just told you. I said Km is the substrate concentration that it takes to get to Vmax over 2. Notice that Km is a concentration. It's not a velocity. It couldn't possibly be Vmax over 2. It's the substrate concentration it takes to get there. Yes, sir? Absolutely. We're doing all these at optimum conditions. Yes, sir?
Practically, how do you know when you're at Vmax over 2?
How do I know when I'm at Vmax over 2? That means I first have to do the experiment to determine where I'm at Vmax. Now, interestingly, when we see that Vmax varies with concentration, is dependent upon the concentration of enzyme, Vmax over 2 does not. Because if I double the concentration, I'm going to double the substrate concentration. I'm going to double this here. This line stays exactly in the same place. So Km is independent of concentration. Km is independent of concentration. It is a property of the enzyme. The property of the enzyme. It's a measure of the affinity, and it's independent of concentration. I've given you now 2 properties for an enzyme. The first property was kcat. That was the turnover number. The second property is the affinity that the enzyme has for its substrate. Okay, I see some scrunched up faces. So questions? Yes, sir?
Is it fair to say that the lower the Km, the higher the Vmax?
Okay, he's trying to compare Km and Vmax, and there is no relationship. Okay? Good question. It's a common question, but there's no relationship between Km and Vmax. Do you have a question? Okay. Yes, sir?
Could you repeat what you said about the independent concentration?
So the Km is not dependent upon the concentration of enzyme. It's independent of that. And I won't go through the derivation. If you want to come by and see it, I'll be happy to show it to you. But Km does not depend on the concentration of the enzyme. Okay? So it's a property. We can say this. If I say I have an enzyme that has a Km of 1 millimolar, that says something. It says it takes 1 millimolar to get to half Vmax. However I measure Vmax, that's what it takes to get to there. Okay? You guys up for a song? Well, actually, let me see. Maybe hold on. Maybe I might be rushing that. I've got one other thing I might want to do first. That way you'll understand the song better. Yes, let's do one more thing, and then we'll do this. We'll do the song. Okay? You have to understand this before you understand some of the things I'm going to talk about in the song. All right? I know it's a lot of sort of techie stuff. I'm trying to put it into real language for you because I believe that math and chemistry are better done in real world terms and in real language than they are as equations and as calculator entries. That's why I'm trying to put these into analogous things for you so that you have a better understanding of them. This one is going to be a little bit of a stretch. Okay? Don't panic. It's the same information you've already seen before. It's only plotted in a different way. Okay? So let's say we just did this experiment I described to you earlier. I said I'm giving you 20 tubes, same amount of enzyme, optimum pH, optimum temperature, all these optimum things, Same amount of enzyme, varying amounts of substrate, right? You have 20 points, you get 20 velocities, and you plot 20 velocities against 20 substrate concentrations, right? That was pretty straightforward, right? Let's say, well, let's take that same information, the same data that you had here, but instead of plotting it as V versus S, let's plot it as the reciprocal, 1 over V versus 1 over S. All that's going to happen is its appearance is going to change. We got the same information, we did the same experiment that we did before. Okay? The beauty of plotting 1 over V versus 1 over S, and by the way, this is called a Lineweaver-Burke plot. Don't worry about the equations. We're not going to have any equations that we're going to use here. Okay? The beauty of this is as follows. What I saw as a hyperbolic before, and this doesn't work for allosteric enzymes, by the way. Okay? What I saw as a hyperbolic before becomes a straight line. And the straight line is very useful because where I had to guess where Vmax was before, does it stop here? Does it go a little higher? Does it not go higher? I can't tell. When I plot it this way, I discover that when I draw that line down to the y-axis, the place where it crosses the y-axis is equal to 1 over Vmax. By inverting the axis, inverting the plots, I can read that value directly off the graph. That value is 1 over Vmax. When I continue drawing that line down into the negative region, I discover that the place where it crosses the x-axis is minus 1 over Km. I now have a very simple way of getting those without having to guess where Vmax is, where Vmax over 2 is, and all of that. Yes, sir. I can't do this for a sigmoidal. It won't give me good results. No. So this is a very useful plot. As I said, it's called Lineweaver-Burke. Lineweaver. That's the first name. And the second name is Burke. B-U-R-K. If I do that, I've got a very simple way of determining Km and Vmax. Same information as before, I just invert everything. So if I had a 5, I make it 1 over 5. If I had a 10, I make it 1 over 10. Make sense? Okay, now we're ready for the song. Yes, question.
You said one, the sigmoidal or the hyperbolic thing has cooperativity, exhibits cooperativity. Which one was it?
So the sigmoidal exhibits cooperativity. Yeah. So a sigmoidal won't work with this analysis. Okay, let me pull it up for you here, and we are set. I want to hear you guys sing loud, because if you don't, we're not going to do songs anymore. Okay? This is to an old tune you may not know, but once I get going, I think you will. It's called Downtown, and the song is called Enzymes. Reactions alone can starve your cells to the bone. Thank God we all produce enzymes. Units arranged to make the chemicals change, because you always use enzymes. Sometimes mechanisms run like they are at the races. Witness the K-cat of the carbonic anhydrases. How do they work? Inside of the active site, it just grabs onto a substrate and squeezes it tight in an enzyme. Catalysis in an enzyme. V versus S in an enzyme. All of this working for you. Enzyme, enzyme. Energy peaks are what an enzyme defeats in its catalysis. Enzymes. Transition state is what an enzyme does great, and you should all know this. Enzymes. Catalytic action won't run wild, don't get hysteric. Cells can throttle pathways with an enzyme allosteric. You know it's true. So when an effector fits, it will just rearrange all the subunits inside and